Yeah. So I welcome you all in this live session 10. So today we will start refrigeration and air conditioning system. So before starting the questions, we will look at the some main concepts in the refrigeration and air conditioning system. So simply we call it as a RAC, refrigeration and air conditioning. Okay. So yeah, to start with, refrigeration system can be divided into two parts. The one is vapor compression refrigeration cycle, and the second is vapor absorption cycle. Okay, so today we will look into both the aspects. Okay, so yeah, to look at the vapor compression refrigeration cycle, so it is opposite to the Carnot cycle or Rankine cycle we talked about in the uh, vapor power cycles. Okay, so here if you see, the vapor compression cycle also consists of four processes. The reversible adiabatic compression that goes from 1 to 2. In the case of power cycle, it was uh, the turbine where the reversible adiabatic expansion were happening. Okay, similarly here is the second process from point 2 to 3, that is reversible constant pressure heat rejection. In the case of power cycle, it was constant pressure heat addition. Okay, the third one is 3 to 4, that is adiabatic throttling process. So that this adiabatic throttling process is different in the case of compression refrigeration cycle. So we will talk about this process separately also. And the fourth process is from point 4 to 1, that is reversible constant pressure heat addition. And in the case of power cycle, it was constant pressure heat rejection. Okay. So basically, vapor compression refrigeration cycle is a reverse Carnot cycle consisting of four processes. Here, from point 1 to 2, this is reversible adiabatic compression. From 2 to 3, it is condensation that is happening at reversible constant pressure. Okay, and heat Q is rejected. Third one is constant enthalpy. H is constant. Okay, you can see here the H is constant here from process in process 3 to 4, that is expansion valve, and it is happening at adiabatic. So this process is adiabatic but not isentropic. So this is not isentropic process but it is adiabatic, and enthalpy H is constant because there is no heat transfer happening and there is no work transfer happening in the expansion wall. And the fourth one is evaporator, where the heat from the, you know, the system where we want the refrigeration effect, the space where we want the refrigeration effect, from where this heat Q is absorbed in the evaporator at constant pressure. Okay, so now one question comes here is, why expansion valve? Why not the, you know, like in the uh, why not the piston arrangement where we can get work from that piston? Because here in the expansion valve we are taking the refrigerant from high pressure to low pressure, right? And we are not getting any work done. So one can ask, why not we put an, you know, turbine or something piston, you know, cylinder piston arrangement where we can expand this liquid and get the work done. Okay, yeah, so that question may arise, but the thing here is, in the case of refrigeration system, if even if we put the cylinder piston arrangement, the work obtained is very less. Okay, because it is going from liquid to vapor, right? And the pressures are not as high as in the case of uh, power cycles. So the work obtained in that case will be very less, and that will not justify the cost and, you know, the bulky structure of this cylinder piston arrangement. So that's why this cylinder piston arrangement is not there, and the expansion valve is there, that is very small part, or capillary is there, that is very small, and we get that desired effect with that, without without increasing the cost or the bulkiness of the whole system. Okay, so that's why we use this expansion valve, not the cylinder piston arrangement. Okay, so this is a basic vapor compression cycle that you already have studied through the videos. Okay, and if we look at the TS diagram of this, so this goes from point 1 to 2. This process is reversible adiabatic compression, where the work W in is given to the compressor. From point 2 to 3 is the condenser. So here the heat Q is rejected while condensing the high pressure uh, refrigerant that is in gas form, that is condensed here. From this point 3 to 4 is the adiabatic throttling process. So the throttling process is constant enthalpic process. The enthalpy doesn't change. Why doesn't change? Because the heat heat transfer Q is 0, work transfer W is 0. So with steady flow energy equation, the enthalpy remain constant. That is shown as point 3 to 4, and from point 4 to 1 is the evaporator. Here is the heat QL is taken by the refrigerant. So this is the refrigeration effect QL we receive in the desired space. Okay, in the refrigerator, we can say that in the refrigerator this QL is given to the refrigerant and refrigeration effect is achieved. Okay, and the one important parameter here in the case of refrigeration cycle is COP, coefficient of performance, that is given by QL by W. So QL is the desired effect, W is the work done on the system. Okay. In the case of heat pump, what is the desired effect? QH is the desired effect. So in the case of COP of a heat pump, this COP of the heat pump will be QH by W. But in the case of refrigeration, COP of refrigeration, it is QL by W, because the desired effect is QL, the heat absorbed in the evaporator, and W further can be written as QH minus QL. Okay, so that's how the coefficient of performance of this vapor compression refrigeration cycle is given. Okay, and if we talk about the refrigerants, so there are various refrigerants. These are based on either ethane based or methane based. So in the case of ethane or methane based refrigerants, the one or more hydrogen atoms are replaced by the either chlorine or fluorine. Okay, so these refrigerants are called as chlorofluorocarbons, CFC. They are, you know, they used to be primary refrigerants for this refrigeration system, but they are detrimental to environment. They cause the greenhouse effect, they result in global warming and all those things. So that's why they were banned due to their greenhouse effect during the Montreal Protocol that happened in 1987. So after that, the alternative refrigerants were, people started looking for alternative refrigerants. So one more refrigerant is refrigerant R134A, that is chlorine free and do not have any greenhouse effect, that is majorly used, and this refrigerant is being used to replace all these chlorofluorocarbons that were being used earlier. And also there is a refrigerant that is ammonia, NH3, and ammonia is you know ammonia NH3 is written as R717, Okay, in the this R717 is given to ammonia, this number. So in the case of ammonia, ammonia is low cost, result in high COP, no effect is there to the ozone layer, and also this has some smell, so it can be detected if there is a case of leakage. But the issue is the ammonia is poisonous, so it is not used for domestic application, domestic refrigerators it is not still used, but it is used in the commercial applications it is used. So this is basic about this vapor compression cycle and the refrigerants. Now we will look at this, what happens in the case of what happens in the expansion valve. Okay, so it is a constant enthalpy process and we will look into it, what happens, how this cooling happens. We are dropping a pressure from high value to low value, and how this dropping the pressure in expansion valve results in the cooling effect. Okay, so let's look at that. So that can be looked upon with the help of Joule Kelvin effect. So in this first figure, you can see there is a porous plug that works as a capillary action, or expansion valve. This work as an expansion valve here. So the pressure, temperature, and enthalpy at the one side, and the pressure, temperature, and enthalpy at the other side. So we can measure the temperature and pressure in the. So this was an experiment, and the result of this experiment are shown in the this graph. So the initial, we took the initial temp at initial fixed temperature and pressure at point I were taken, and the gas was expanded at different pressures and temperatures. So these points achieved, and this is a graph of constant enthalpy graph between T and P. You can see in the third figure. Okay, so now you can see how this gas behaves when it is, the pressure is dropped in the capillary or expansion. What happens, how this behaves. Okay, so from this constant enthalpy curve between T and P in the third figure, you can see this is the behavior when we expand the gas, and the slope of this curve, that is called as Joule Thomson coefficient. Okay, mu jt, that is defined as del T by del P at constant enthalpy, right? So this Joule Thomson coefficient is defined as the slope of this curve. Now, this curve shows uh, the one condition of pressure and temperature, the initial temperature and pressure. Okay. Now, what if this this experiment was performed multiple times? So what type of graph was achieved? So here you can see in the lower bottom, lower left bottom, so these multiple graphs were achieved. So here you can see at this point, at the highest point, the slope is 0, and this mu jt is 0, right? Now if we go beyond this into the left side, you can see the slope is positive. Slope is positive means if pressure increases, temperature increases. Okay, so in the case of expander, porous plug, or capillary action, we always drop the pressure. So here in this region, as the pressure drops, the temperature will also drop, then only the value of mu jt will be positive, right? So in this region, the Joule Thomson coefficient is positive. That means in this region, if we drop the pressure using porous plug or capillary action, then always the cooling effect will achieve. But in this case, in this side, only heating will achieve. Okay, and this phenomena can be seen here in the figure, this figure. Okay, so here you can see for the multiple initial conditions the multiple graphs we achieved. So here the the so this point here where the Joule Thomson coefficient is 0, that is called as inversion point. Okay, so now if we plot the inversion points for multiple initial conditions, we get this inversion curve. Okay, so inside this inversion curve, this is the region of cooling. If we operate in this region, always the cooling will occur, and outside this region the heating will occur, and on this curve there is no cooling or heating effect. So what happens in the expander or expansion wall, the gas or refrigerant is always uh, the always work in this region of cooling. The pressure is always dropped from somewhere close to this inversion point to the left side, left part, and the cooling will occur. Okay, so this is how the cooling effect occur in the case of refrigeration cycle in the expander or expansion wall. Okay, so this is how the cooling will occur. So this is based on Joule Kelvin effect. Okay, so this is all about the vapor absorption cycle as well as the Joule Kelvin effect, which results in the cooling of the refrigerant when we drop the pressure in the capillary or expansion wall. Okay, now the second type of refrigeration cycles are the vapor absorption cycle. Okay, so let's look at that also. So absorption refrigeration cycle. So if you see, there is a condenser, expansion wall, evaporator, but in place of compressor there is this generator and absorber. Okay, so in the case of absorption refrigeration cycle, the compressor is replaced by absorber and generator assembly. First thing. The second thing is, here the Q is given in the form of heat. Okay, so the energy supplied to this refrigeration cycle is in the form of heat, and heat is a low grade of energy. So absorption cycle work on low grade of energy, or absorption cycle are heat operated cycle. Here the compressor is replaced by absorber generator assembly, and what happens here is, in the case of absorption cycles, there are two elements. The one is absorbent, the second one is refrigerant. Okay, so what happens is, when the refrigerants come out from the evaporator, it is at low pressure. At low pressure it has an affinity to get absorbed in this absorbent. So here in the absorber, when this refrigerant comes, it get absorbed in the absorbent, due to which the this latent heat of condensation releases, and this heat is taken by the cooling system, take and it is rejected to the atmosphere. Then this you know this mixture of refrigerant and absorbent is pumped back to the generator. Okay, in the generator the heat Q is supplied. Due to this heat Q, the temperature increases, and as the refrigerant has a lower boiling point compared to the absorbent, it get evaporated first and goes to the condenser, and the remaining absorbent is sent back to the absorber again, and this cycle continues, and this refrigerant goes to the condenser, condenses there, then expanded in the expansion valve, goes to the evaporator, takes heat from the refrigeration space, and then goes back again to the absorber and generator assembly. Okay, so that's how this absorption refrigeration system works. Now we have two type of absorption cycles. The first one is aqua ammonia absorption system, here where the ammonia is refrigerant and water is absorbent. So in the case of aqua ammonia absorption system, the ammonia works as refrigerant. It The low pressure ammonia goes to the absorber. It get absorbed into the water, because in the absorber there is this weak solution of ammonia water solution. Okay, so this low pressure ammonia get absorbed in the absorber. The latent heat of condensation is given out to the atmosphere. This strong solution is sent to the generator, where the q in the heat is applied to this strong solution. The ammonia, having lower boiling point than water, boils first, evaporates first, and goes to the condenser, and the remaining uh, weak solution of ammonia water goes back to the absorber, and this way this cycle continues. Okay, so that is the aqua ammonia absorption system. And the second one is the lithium bromide water absorption system. So in the case of lithium bromide and water absorption system, water works as refrigerant and lithium bromide works as absorbent. Okay, so here the uh, the water, the behavior of water changes. In the case of aqua ammonia, it was working as an absorbent, and in the case of lithium bromide water, it is working as refrigerant. But now, as it is working as refrigerant and water cannot go below 0 degree centigrade, so this system cannot be used for refrigeration applications, but this can only be used for application in air conditioning only. So this system is used for ACs only. Okay, so this is a brief about the absorption refrigeration cycle. So any questions till here you can ask, then we will move to the assignment part. Anyone, any questions?
No, sir.
Okay, so we will move to the assignment part. We will look at the questions. Okay, so now the first is the condensation process of refrigerant in a vapor compression cycle is carried out at constant blank space. Okay, so the condensation process of refrigerant. So in the vapor compression cycle, we saw one was the adiabatic compression, the second was reversible constant pressure, right? Constant pressure condensation. Again, adiabatic expansion and reversible constant pressure evaporation. So condensation happens at reversible constant pressure, right? So here the first option is wrong, the second one is right, third is wrong, and fourth one is wrong. So in the case of vapor compression cycle, the condensation process happens at constant pressure. Okay, so yeah, this was very simple concept based question. Now the second one is, in the expansion process of refrigerant in the throttle valve of a vapor compression system, which of the following thermodynamic parameter doesn't change? So we are talking about expansion process in the throttle valve. So we talked about it in detail in a full slide, that the expansion in throttle valve happens at constant enthalpy. Okay, so enthalpy doesn't change from this steady flow energy equation. It is already given that the expansion in throttle valve happens at constant enthalpy. Enthalpy doesn't change. Other parameters can be changed. So density is wrong, specific volume is wrong, but specific enthalpy remains constant. That doesn't change in the case of expansion process in throttle valve. So throttle valve can be throttle valve, porous plug, capillary tubes, that can be anything. But in the case of expansion process, it happens at specific constant specific enthalpy, and enthalpy doesn't change. Okay, yeah. So let's move to the next one. So this next one is, in an actual vapor compression system, the refrigerant temperature in the evaporator is higher than the cold region temperature. Okay, so let's see. There, what question says is, this is evaporator. Okay, and this whole is the cold region. So what happens in the evaporator is, evaporator takes heat from this cold region, right? This is the work of evaporator. So in the case of evaporator, refrigerant flows refrigerant flows, and in the evaporator the heat is taken from the cold region by the refrigerant. So this heat only can be taken if the temperature of evaporator is lower compared to the cold region, right? Here in the question it is said that the refrigerant temperature is higher than the cold region. Say if the temperature of this evaporator is considering 350 Kelvin and the cold region temperature is 300 Kelvin, so in which direction heat will flow? Heat will always flow in from high temperature to low temperature. But in the case of evaporator, heat flows from the cold region to evaporator. So evaporator temperature should be less than the cold region temperature, right? So this statement is false. So in the case of actual vapor compression system, the refrigerant temperature in the evaporator is lower compared to the cold region temperature. This cannot be higher. Okay. So this statement is false. Any doubt?
No,
No,
sir.
sir. Yeah. So let's move to the next one. So this next one is, which of the following cooling device doesn't use low grade energy? So very first we have to revise what is the low grade of energy. Heat is the low grade of energy. And what is the high grade of energy?
Work.
Yes. So work is high grade energy, the shaft work, the electricity, that is also a high grade energy. The mechanical work is high grade energy. Okay. So now
Yes,
we
sir.
have to look which of the devices doesn't use low grade energy. Okay. So we want to look at some devices in which the heat is not used, only the direct energy is used. Okay. So in the case of vapor compression heat pump, so in the case of vapor compression heat pump, there is work done on compressor. So work done is in this form of electricity, right? So this is high grade energy. HGE, high grade energy. So this is the correct option. In the case of gas cycle refrigeration system, the fuel burns, heat releases. So these use heat, that is low grade energy. Ammonia water vapor absorption system and lithium bromide water. So both the absorption system also uses low grade energy, and this also uses low grade energy. So what is the right option? The first one is the right option, where in the case of vapor compression heat pumps, the work is given in the form of electric energy, that is a high grade energy. And question asks, which of the following cooling devices doesn't use low grade energy? So the option 1, the option A is the right option. Okay.
Okay, sir.
Let's move to the next one. So the next one is based on absorption refrigeration cycle. So here the question is, lithium bromide, being a salt, has strong affinity for water vapor because of its very low vapor pressure. So this is kind of a statement that is a fact. Okay. So in the case of lithium bromide water absorption cycle, the lithium bromide work as an absorbent and water works as a refrigerant. Okay. So this lithium bromide has a very strong affinity for water vapor, and the only reason for that is the lithium bromide has a very low vapor pressure, and that's why it has this strong affinity. So this is a kind of fact, and there is nothing to nothing much to explain this statement. This is a direct statement, and this statement is true. Okay. So lithium bromide, yes, lithium bromide has a strong affinity for water vapor, and the sole reason for that is very low vapor pressure of the lithium bromide. Okay. So this is kind of fact. Let's move to the next one. Yeah. So for an ideal vapor compression cycle consisting of compressor, condenser, throttling valve, and evaporator, which of the following components undergo a reversible process? So as we have already seen this thing in the initial second, third, fourth slides. So we have seen that for ideal vapor compression cycle, the compressor works on reversible, isentropic, or adiabatic. Okay, reversible, adiabatic compression, right? The condenser also works on reversible, constant pressure. The throttling valve works on constant enthalpy or adiabatic expansion, and evaporator works on reversible, constant pressure. So in the case of compressor, condenser, and evaporator, all these three components works on reversible, adiabatic, or constant pressure processes. But in the case of throttling valve, this throttling valve works on adiabatic expansion that has a constant enthalpy throughout, but this is not a reversible process. Okay. So out of four, only three processes are reversible processes, and throttling wall is not a the throttling wall doesn't work on a reversible process. Okay. So the option C, or option third, is the correct answer for this question. Yeah. So the next one is the trade or commercial name of ammonia refrigerant is. So as we saw in the initial slides, The ammonia is given the commercial name R717. So this is the NH3 ammonia. Okay, so option 1 is the right, and here you can see option D as R444. So if you remember, this R44 is CO2, the carbon dioxide. So the carbon dioxide is given R744, and the ammonia is given R717. So the name of ammonia refrigerant, the commercial name of ammonia refrigerant is R717. Okay. So again, this is a pretty simple question. Let's move to the next one. Yeah. So this question number 8 is a small numerical. So what it says is a heat pump operates on a reverse Carnot cycle. Okay, reverse Carnot cycle पे work कर रहा है. The temperature in the condenser coil is 27 degrees centigrade, and that in the evaporator coils is 23 degrees centigrade. For a work input of 1 kilowatt, how much is that heat pumped from the low temperature reservoir? Okay, so let's first make a schematic. Okay, so it is a evaporator, and this is the condenser. So the condenser works on 27 degrees centigrade, that can be written as 300 Kelvin, and this works at evaporator works as minus 23 degrees centigrade, that can be written as 250 Kelvin. Okay, and also 1 kilowatt of work is given to the heat pump. Okay, so now the question asks, so a heat pump is working on reverse Carnot cycle. The condenser temperature is 300 Kelvin. The evaporator temperature is 250 Kelvin. 1 kilowatt of work is given. So how much is the heat pumped from the low temperature reservoir? Okay. So we already seen the coefficient of performance. So what is the coefficient of performance? So for refrigeration, the coefficient of performance is the desired effect. Okay, so QL is a desired effect divided by W. Okay, and that can also be given as TL by W, and that can be given as TL divided by TH minus TL. Okay, temperature of uh, hot environment divided by minus temperature of uh, 1 minute, temperature of cool environment. So the COP can be calculated as TL. What is TL here? TL is 250 Kelvin divided by TH is 300 Kelvin minus 250 Kelvin, that is given as 250 divided by 50, that comes as 5. So COP of refrigeration comes as 5. Okay, so what it means is 5 is the 5 is equal to QL by W, and W is given as 1 kilowatt. So QL is 5 kilowatt. Now we need to understand that a heat pump is working between 250 Kelvin to 300 Kelvin, works as a reverse Carnot cycle. 1 kilowatt work is given. Okay, and 5 is the COP of refrigeration. Okay, so for COP of refrigeration it is 5, but if we want to calculate the COP of heat pump, then what will be the desired effect? The desired effect will be the heat given to the condenser, right? Heat given to the condenser, that will be the desired effect, means TH, hot environment, divided by TH minus TL, and that will be 300 Kelvin divided by 50 Kelvin, that will be 6. Okay, so COP of heat pump is 6, COP of refrigeration is 5, and 1 kilowatt work is given. Okay, so basically it takes, yeah, so basically it takes 5 kilowatt from here and gives 6 kilowatt here, and 1 kilowatt is the work that I did from here only. Okay, so let's look at the question again. So for a work input of 1 kilowatt, how much is the heat pumped from the low temperature reservoir? So heat pumped from the low temperature reservoir is 5 kilowatt, and heat pumped to the high temperature reservoir is the 6 kilowatt. So in the question, the heat pumped from the low temperature reservoir is asked. So answer is the 5 kilowatt. Okay, so 5 kilowatt is the amount of energy that is pumped from the low temperature reservoir, and reservoir is at 250 Kelvin. Okay, so the answer is 5 kilowatt. And if it was asked how much energy, how much is how much is the heat pumped to the condenser or to the high temperature reservoir, the answer could be 6 kilowatt. Okay, yeah, so any doubt in this question? This is a like very simple but conceptual question. So any doubt, anyone, any doubt, you can ask.
No, sir.
No sir, all clear. Okay, so we will move to the next one. Yeah, so the next one is, in a lithium in a lithium bromide water vapor absorption system, water is used as absorbent. So tell me, it is true or false? I explained it earlier. Someone told, tell me, it is true or false. So lithium bromide water vapor absorption system, water is used as absorbent or uh, refrigerant. Anyone? Neelam,
True,
Abhishek.
sir.
What? What, Kashish?
It is true statement, sir.
Uh, Anyone else? Neelam or Payal or Abhishek? Okay. So let me answer. So in the case of lithium bromide water vapor absorption system, water is used as refrigerant. Okay. In the case of ammonia water, it was used as absorbent, but in the case of lithium bromide, it is used as refrigerant. So this statement is false. Okay. So in this case of lithium bromide and water vapor absorption system, water is used as refrigerant and lithium bromide is used as absorbent. And this is the reason that this lithium bromide water system can be used for air conditioning only, that cannot be used for uh, refrigeration purpose, because the water has a limitation that it cannot be cooled below 0 degree centigrade, right? So that's what we discussed in the third fourth slide. Okay, so Kashish, your answer was wrong. The water is used as absorbent in the case of lithium bromide water system. Okay,
Okay, sir.
yeah. So let's move to the final question. Yeah. So here in the case of lithium bromide water absorption system, water works as refrigerant and lithium bromide works as absorbent. Okay? Yeah. So the final question is, in an ammonia water vapor absorption refrigeration system, with the increase in concentration of ammonia in the absorber, the solution temperature decreases. Okay.
Yes,
So
sir, that's true, sir.
yeah, it is true. And who answered? Payal or Neelam? Who answered? Payal.
Sir, I got.
Yeah. So Payal, why the solution temperature decreases? Any guesses?
Because ammonia is a refrigerator for this case.
Yeah, ammonia is refrigerant in this case, but with the increase of concentration of ammonia, why the solution temperature decreases? Yeah, so let me answer you. So what happens in an absorber? There is a weak solution of ammonia water is available, and from here, from evaporator, the low pressure ammonia goes to the absorber. So ammonia has a uh, high affinity for this water, or weak solution. So it gets absorbed in this weak solution, and releases the latent heat of condensation. Okay. So this latent heat of condensation it releases, and it tries to increase the temperature, and this latent heat of condensation is taken out by some cooling system or cooling water. Okay, that happens. But in the case of, if we increase the concentration of ammonia in the absorber, so there will be less affinity for the low pressure ammonia to mix with this strong solution. So means low amount of mixing, low amount of ammonia getting absorbed means low amount of latent heat of condensation release. That means low increase in the temperature, or the decreased solution temperature. Okay, that is the main reason. So your answer was right. Okay, but the explanation was needed. Okay. So
Sir, please say again what you say.
okay, so forget about the question, forget about the question. I will repeat the concept again. Okay. So the concept is, so the concept is, let me go to the slide. Here is the slide. Okay. Yeah. So this is the absorption cycle. So what happens here is, in the case of ammonia water system, let me change the color. Yeah. So in the case of aqua ammonia or ammonia water system, the low pressure ammonia vapor comes from evaporator. Okay. This ammonia vapor goes to the absorber, and in the absorber there is already a weak solution of ammonia water. Okay. Weak solution means the concentration of ammonia is very small in the water. Okay. That's why we call it as a weak solution. So there is a weak solution of ammonia water. From here, the pure ammonia at low pressure goes inside the absorber. At this low pressure, it has a strong affinity for water, so it gets absorbed in the water. As it gets absorbed in the water, this low pressure ammonia vapor converts into liquid form. Okay. So when it converts into the liquid form, it releases the latent heat of condensation, right? So
Yes, sir.
so the release of latent heat of condensation results in increased temperature of this whole solution, right?
Yes, sir.
Yeah. So this increased temperature of this whole solution means we need to reject this amount of heat to keep this the temperature of the solution in the limits, right? So this latent heat of condensation is given out to the atmosphere by some means of cooling water or something. Okay, so this heat
Okay,
is
sir.
given. Yeah. So now the amount of this heat release, this latent heat of condensation, again depends on how much amount of ammonia is being absorbed in the water, right? So low
Yes,
absorption
sir.
means low heat release, high absorption means high heat release. And again the absorption amount also varies with the concentration of ammonia already present in the water. Okay, so high amount of ammonia present means low amount of absorption, low amount of ammonia present means high amount of absorption. Okay, so this is the concept. I would say forget about the question, remember this concept. Okay. Okay, Kashish.
Yes, sir. Okay.
Yeah, you got the concept, right? That is important.
Yes, sir.
That is important. So this was all about this session. If you have any doubt from this session, you can ask anyone any
Sir, I
doubt.
have
Should
a
we
one doubt.
Yeah, yeah. Payal, ask any doubt.
please go to the
I cannot hear you, Payal. Can you speak clearly, loudly?
sir, please go to the first page.
First slide. Okay. This is the first slide.
Okay, sir. Thank you.
Okay. Yeah. Kashish, you were asking something?
Yes, sir. I have a doubt. Sir, centrifugal compressor are preferred for low evaporator pressure
Yeah.
and represent with a large specific volume at lower pressure. Sir, what are saying in this question?
So, can you repeat that question again?
Yes, sir.
Um,
Centrifugal compressor are preferred for
yeah.
low evaporator compressor and represent with large specific volume at lower pressure.
Yes. Yes. So, yeah, this is a right statement. Yes, because for higher amount of volume, okay, for higher amount of volume, these centrifugal compressors are used. Okay, so at low specific pressure or high specific volume means for a given amount like 1 kg of or 1 kg of refrigerant, the volume will be very high. Okay, so to to handle that much amount of the volume, you need a centrifugal compressor. Otherwise, for a reciprocating compressor, you need a big compressor and that is not economical, as well as that makes the system bulky, so that is not recommended and used. Okay, so the centrifugal compressors are used to handle the large volumes at low pressures and high specific volumes. Okay, so the statement is correct. Okay, so high amount of volume means you need a centrifugal compression. So basically, in some simple terms, if I tell you, so if the volume flow If the volume flow rate of the refrigerant is high, then we use the centrifugal compression. Okay. So
Okay, sir.
yeah. So yes, Payal, I can share. So it is a okay. So it is Akhilesh Goyal 93 at gmail.com. So I have shared my email ID in this message, in call messages. So you can look at that. And if you have any other doubts, we can continue. Otherwise, I will close the session right here. Okay. So anyone, any final doubts? So considering there is no doubt, I am closing the session. Okay.
Okay, sir. Thank you.
Thank
Yeah.
you, sir.
Yeah. Thank you, everyone.